Come on, my dears. Today we begin with chapter number 3 on electromagnetic waves. My dears, this chapter is very useful, not only from syllabus point of view, in our day-to-day life also. The importance of electromagnetic waves is perhaps maximum. How? I am showing you. What are called electromagnetic waves? How they can be produced? What are their properties? What are their applications or uses in our day-to-day life? We will study everything in detail in this chapter. But first of all, let me realize you about the importance of study of electromagnetic waves. What is the physical importance? I am showing you. First of all, to see any object. See, Almighty has prepared very beautiful world around us, and Almighty has donated eyes also in our body. We have eyes, we have surrounding beautiful world, but let me tell you, you can see any object, any scene you can see with the help of visible light waves. Human eye is sensitive for visible light waves. So, let me tell you, visible light waves are nothing but, in this chapter we will study, they are electromagnetic waves. So, when you can see anything, that credit goes to electromagnetic waves, correct? So, seeing, watching anything is possible only because of electromagnetic waves. Now, you can realize its importance, correct? Fine. What is the second point? Second point is this: to receive heat or warmth. We receive necessary heat or warmth for our existence in the form of infrared light rays, which are emitted from sun. Okay, they are responsible for spreading the heat. That's why sometimes we call them heat rays. They are also electromagnetic waves. Fine. Point number 3, existence of our life is due to electromagnetic waves. Now you may wonder how. Let me tell you, you and me, we all are existing because we take in, we breathe in what? Oxygen. Can you and me survive in the absence of oxygen? No, we cannot survive. And that oxygen, the main source of production of oxygen gas, you know, it is through plants and trees. It is through green life, and that oxygen is generated in this green life because of process of photosynthesis. Now you must have studied in your lower standards in biology that for photosynthesis process, sunlight is essential. And let me tell you that sunlight is nothing but electromagnetic waves. So from this whole universe, if you discard sun, then you will not have any sunlight, no photosynthesis, no generation of oxygen gas, then we cannot survive. So, credit of our existence goes to electromagnetic waves. Now, you must have realized that it is the first step required for our existence, that is electromagnetic waves, correct? Fine. Point number 4, for medical treatment, we use different types of electromagnetic waves, different types of radiations, about which we will discuss the things in detail in the later part of this chapter. So, in the medical treatment also, electromagnetic waves are very useful. And point number 5, for modern communication. See, at present, the communication has so much advance that over the entire globe of earth, any person, anywhere can just immediately contact any other person, might be lying anywhere, correct? So such a global communication is made possible, let me tell you, due to production, propagation and reception of electromagnetic waves. If electromagnetic waves are not generated in laboratory, in some devices, then we cannot enjoy any such mobile phone services, correct? So that credit of modern telecommunication goes to electromagnetic waves. So our luxury is grateful to these electromagnetic waves, correct? So these are the various points from which you must have realized the study of electromagnetic waves has maximum importance. Fine. Now let us see brief history of electromagnetic waves. Who had thought about these waves first? How he entered in this story? He was none but Mr. Maxwell, very great physicist of his times. Mr. Maxwell, you know what he was doing? He was just studying the relationship between laws of electromagnetism such as Gauss law, Amperes law, Faraday's law, etc., and the closed loops formed by magnetic field lines. He was studying such topics, and whatever study he had made, that study he had expressed in the form of 4 differential equations, which were later known as Maxwell's differential equations, or shortly Maxwellian equations. Fine. Now when Mr. Maxwell had examined those 4 differential equations from symmetry between electric and magnetic field point of view, at that time he realized that in one of the 4 equations, which was known as Amperes law, he found that certain term is missing. And what can be that missing term? Mr. Maxwell had found out that term, and he had added that term, and he had made that equation completed. That missing term, which was later on found out by Mr. Maxwell, it was given a specific name. That specific name is displacement current. Fine. And after adding that missing term, once again Mr. Maxwell had examined those 4 differential equations. At that time he realized that these differential equations are none but wave equations. So when he saw these wave equations, he was really astonished, he was really very much surprised, and then looking at those wave equations, he simply had predicted that now in practice, in our day-to-day life, there must be existence of some waves which can satisfy these wave equations. So those represented waves, they were represented by those equations. These waves must be existing in practice. That was the prediction made by Mr. Maxwell. He said that when these wave equations are existing, then those waves must be existing in practice which can satisfy these equations. Fine. Now, how were those waves? In those equations, Mr. Maxwell had talked about time varying electric field and time varying magnetic field. Because there were variations in electric and magnetic field involved in such waves, he had given name of such waves as electromagnetic waves. Fine. But he had simply predicted, because he was a theoretical physicist. He never went in laboratory, he never proved it experimentally. No, he simply had predicted that such waves must be existing, which are represented by these wave equations. Fine. But he was so much confident in his prediction that he went ahead in his research and he had proved that in future, whenever the existence of such waves will be proved, what could be its velocity of propagation in vacuum. That formula he had derived, and that formula is this: C equals to 1 upon under root of epsilon 0 into mu 0. What is epsilon 0? Everybody knows, permittivity of vacuum. What is mu 0? Permeability of vacuum. When he had substituted these values and then after he had simplified, he got this value as 3 into 10 raised to 8 meter per second. And in his time also, in the time of Maxwell also, the velocity of light in vacuum was known, and that velocity was also same. So he had made another prediction that perhaps light waves also may be electromagnetic waves. So in all he had made 3 predictions. Number 1, there must be existence of waves in which there are time-varying electric and magnetic field called electromagnetic waves in practice. That was the first prediction. Second prediction, its velocity in vacuum must be 3 into 10 raised to 8 meter per second. And third prediction, that light waves also must be electromagnetic. You will not believe, 32 years after the prediction of Maxwell, Mr. Hertz, in the memory of whom we had given the unit of frequency, same fellow, Mr. Hertz, had proved all these predictions 100% correct. So Mr. Maxwell was such a great physicist that all the 3 predictions came out to be true in reality, and that credit goes to Hertz because he had initiated, he had proved it experimentally first. Got it? Now, before we go for Hertz experiment, there are some other various topics to be discussed. Among them, first is about that missing term. What was that missing term? Known as displacement current. Let us study now in detail what is that displacement current, how does it arise. I am showing you. To understand about displacement current, you just consider a capacitor connected with a battery. Look here. Here is one capacitor which is connected across a battery. Fine. You know what will happen now onwards? Capacitor will get charged up gradually. How? I am showing you. This plate which is connected with a positive terminal of the battery will lose the electrons because those electrons are attracted towards this positive terminal. So after losing electrons, this plate would become positive. Those electrons which are entering into the battery will receive energy from the battery, will be deposited on this plate now, that is plate B. Because excess electrons are deposited on plate B, it becomes negative. As time passes on, more and more electrons are transferred from plate A to plate B, and so positive charge on plate will go on increasing, negative charge will go on increasing on plate B. I mean to say, positive charge on plate A, negative charge on plate B will go on increasing with time, means the process is said to be charging of a capacitor. So right now this capacitor is getting charged up. Fine. Now if electrons are flowing this way, correct, in just opposite direction, we think of electric current. That current we just show it this way, correct, away from this positive terminal, this way. Fine. Now up till now we were calling that current as electric current only, but now onwards in this topic we will call it not only current, we will call it now onwards as conduction current, which flows in this solid wire, correct? Which flows in solid conducting medium, we call it conduction current. Now there is a problem. What sort of problem I am showing you? This conduction current flows up to this plate only. So it enters in plate A, but then no current comes out of plate A, and yet current is flowing away from plate B, though there is no entering current. Here there is no outgoing current, here there is no incoming current, and then also the current is flowing in the circuit. So this shows discontinuity in the flow of electric current. If really current will become discontinuous, then Kirchhoff's current law would fail. Kirchhoff's current law, that is called KCL, Kirchhoff's current law, KCL, Kirchhoff's current law would fail. Then how to explain the continuity of electric current? Because if you consider all these components connected one after another in series, then you know for the components which are connected in series, current passing through all of them must be same. And here we get conduction current in this wire and up to this plate only. And here from this plate onwards again that conduction current starts. But if there is no flow of electric current between these two plates, then current flow would become discontinuous. Then how to explain the continuity of current? Come on, tell me, what is the electric field which has been generated between these two plates? You know that formula? Capital E equals to sigma upon epsilon 0. Sigma upon epsilon 0. What is sigma? Surface charge density, that is total charge upon total area. Come on, total charge on one plate at one point of time is suppose Q, and surface area of that plate is A. Fine. So sigma is Q by A. Now just take dE by dt. dE by dt. Why we take dE by dt? Because here epsilon 0 is constant, A is constant, but during the charging process of a capacitor, charge on capacitor goes on increasing. As this will increase, naturally strength of electric field will also increase. So there is a variation in the electric field between the plates. That's why we are thinking of time rate of change of electric field. For that, mathematically, we take derivative of E with respect to time. Just take it on both the sides. So here it will be dE by dt. Here 1 upon epsilon 0 A, that much part is constant, taken out, 1 upon epsilon 0 A, and then take d by dt here. So it would become dq by dt. Fine. Now find out dq by dt. Epsilon 0 A you can transfer here. Epsilon 0 A into dE by dt. Fine. Now this part as it is, epsilon 0 as it is. Now you can just take this A inside the symbol of derivative because it is constant. So now you can rewrite d by dt of A into E. d by dt of A into E. But you know very well, this area into electric field is going to give you electric flux shown by symbol phi E. So epsilon 0 as it is, d by dt as it is. In place of this, I just write phi E, that is electric flux. Now tell me, this has the unit coulomb, this has the unit second. So coulomb upon second, don't you know? It is ampere. Coulomb upon second is ampere. And ampere is the unit of electric current. But this is that current. This is that current which has been produced because of time varying electric field. Because of time varying electric field. See, up till now you were talking about conduction current, that is because of drift motion of free electrons. Because of drift motion of free electrons. Now, such a current is not due to drift motion of free electrons, because there is no movement of electron between these two plates. Between these two plates there is no movement of electron, correct? This is the current which has been produced because of time varying electric field. Means this current is different than conduction current. The different current we have given different name, and that different name is displacement current. And that displacement current is shown by symbol ID. D you should write as a suffix well below I. Got it? So now this is going to give you that current which has been produced because of time varying electric field. We will call it displacement current, shown by symbol ID. Correct? Fine. Now, in place of dq by dt, I am writing ID. Let me write it here. Correct? In place of this dq by dt, if I write ID, then formula is epsilon 0 A dE by dt. Epsilon 0 A dE by dt. Fine. Now tell me, take this A down. Correct? So ID upon A, that will be epsilon 0 into dE by dt. Correct? But tell me, what is current upon area? Current upon area would give you what? Electric current density. Electric current density. But this is displacement current density. So I am just showing it by symbol JD. D again below J. Okay. What is this JD? Electric current density? No. Displacement current density. Because here we are adding displacement current. Okay. Fine. Now, same ID formula I am writing here. Correct. Epsilon 0 A. But instead of dE by dt, as per the textbook, I am writing del E by del T. Why I am writing del E by del T? You must be knowing del by del T gives you partial derivative, partial differentiation with respect to time. See here, electric field, if it depends on more than one variable, then we are interested in finding out variation of electric field only with respect to time. So we are less concerned with the dependence of electric field on other factors. We are concerned with dependence of electric field on time. That's why out of many possible derivatives, if we are taking derivative with a particular variable, then we call it, come on, partial derivative. It is not the total derivative. That's why I am putting symbol of partial derivative, del E by del T. Got it? Fine. Now this ID as it is, epsilon 0 as it is, del E by del T as it is, correct? And now instead of A, I am just putting integration, come on, vector dA. Fine. Instead of this area, I am just putting integration vector dA. So you may write formula of displacement current in the differential form like this, or in integral form like this. This is differential form, this is integral form, okay? And dot product between these two vectors will give you scalar. So this is the formula written in a scalar form, this is the formula written in a vector form, but dot product between these two vectors will give you scalar. Got it? So don't forget to put here dot, you must put this dot, okay? Fine. Now what is the meaning of electric current in a limited sense? Up till now, whatever concept we had developed in our mind regarding electric current, that was from limited point of view, limited viewpoint. What was that limited viewpoint? Up till now we were taking current as flow of electrons just in the direction opposite to direction of electric current. That's all. But now onwards we should just give broad meaning of electric current. Let us generalize this concept. What is wide meaning of electric current? See, whether it is conduction current or displacement current, they both produce magnetic field. See, conduction current produces magnetic field, that you know very well, because current is a source of magnetic field. And displacement current gives rise to, or it is due to, time varying electric field. It is due to time varying electric field. When you have electric field in space which varies with time, it would induce magnetic field. Time varying electric field induces magnetic field. So ultimately, displacement current also produces magnetic field. So remember, wide meaning of electric current is that which can produce magnetic field. Anything which can produce magnetic field can be taken as flow of electric current. Might be conduction current, might be displacement current, no problem, correct? That is the wide meaning of electric current. Fine. Then we go for generalized form of Amperes law for magnetism. See, in third semester you had studied Amperes circuital law, and that law was mathematically expressed this way: closed integration of vector B dot vector dl is equal to mu 0 into I, mu 0 into I. But what was that I? That was a current passing through some wire, means it was ultimately conduction current. But that was not sufficient, that was not giving you continuity. So just to have the continuity in the circuit, we need to add another current with conduction current. That current was found out by Mr. Maxwell, and the name you know very well now, displacement current. So don't write simply I or IC, you add displacement current to that current, then the whole circuit will be continuous and you can apply this Amperes law. If you write Amperes law in this form, we call it generalized form of Amperes law, or sometimes it is called Maxwell-Amperes circuital law. Maxwell-Amperes circuital law. Okay, fine. What is the physical importance of displacement current? Physical importance is in two ways. There are two physical importance points. First point is that using this displacement current, you can explain the continuity of electric current in open circuit like this, correct? Ultimately, what happens here? Current is becoming continuous, then you can say in all the parts which are connected in series, the current is same. So you can explain the continuity of electric current only if you develop the concept of displacement current. And second point is that using displacement current only, you could give generalized form of Amperes law. If you don't express this displacement current, in some of the cases, this Amperes law would fail. If you add this term, then Amperes law becomes very general, right? Fine. Then let us give one very good, very short extra proof. At any point of time, whatever is the value of conduction current in a circuit, same is the value of displacement current in that circuit. How to give such a proof? I am showing you. First of all, you just consider either of these two plates of a capacitor which is getting charged up. Suppose I am considering at present plate A. The same plate I have shown here. This is plate A. Fine. Then in addition to this plate, just surrounding to that plate, I have imagined one closed surface. In 3 dimensions, you just consider such a closed surface. I have written here closed surface. Fine. Now tell me, what is the current entering here? Current entering here into this plate A, that is conduction current IC. So this current is conduction current IC. And what is the current which comes out of plate A and it is flowing between plates A and B? That is none but current due to time varying electric field. It is none but displacement current. That's why I am just showing here displacement current ID, which comes out of this closed surface. Fine. Now tell me, at a given point of time, suppose charge on this plate is say Q. So you can say that is a charge which has been enclosed from all the sides by this closed surface. And if Q is the enclosed charge, if you divide it by epsilon 0, it will give you electric flux according to Gauss theorem. Phi E equals to Q upon epsilon 0. Transfer this epsilon 0 here. So you will get Q equals to epsilon 0 into phi E. Fine. Now take d by dt on both the sides. So here dq by dt, here epsilon 0 is constant, and here d phi E upon dt. Tell me, what is this? Time rate of flow of electric charge. Time rate of flow of electric charge through this conducting wire. And time rate of flow of electric charge through a conducting wire gives you conduction current, shown by symbol IC. And what is this? Epsilon 0 d phi E upon dt. Epsilon 0 d phi E upon dt, what is it? Displacement current ID. So this is displacement current ID. So what we have proved? At any point of time, whatever is the value of conduction current, same is the value of displacement current. Got it? Let us now prove that unit of displacement current is ampere. Let us prove. Simple. Unit of displacement current means unit of this term, that is epsilon 0 d phi E upon dt. Here it is. Epsilon 0 d phi E upon dt. Write unit of each quantity. Come on, epsilon 0, permittivity of vacuum. What is the unit for that? You must remember the value, 8.85 into 10 raised to minus 12. And with that value, what was the unit we were speaking all the while? Coulomb square upon Newton meter square. Coulomb square upon Newton meter square. Here it is. Coulomb square upon Newton meter square. What about electric flux? It has the unit Newton into meter square upon Coulomb. Newton into meter square upon Coulomb. Don't forget to write unit of time in the denominator, which is second. Now simplify. 1 Coulomb is getting cancelled, correct? Still 1 Coulomb is left. Newton is getting cancelled, meter square also getting cancelled. What is left out? Coulomb upon second. Coulomb upon second is nothing but ampere, correct? So unit of displacement current we have proved it is ampere. Let us take one more extra question. Mention 2 points of difference between conduction current and displacement current. First, how do they arise? Conduction current is due to drift motion of free electrons in a conducting medium. I repeat, conduction current is due to drift motion of free electrons in the conducting medium. What about displacement current? It is produced due to time varying electric field. It is produced due to time varying electric field. What is the second point of difference? Conduction current always flows in a conducting solid medium, and this displacement current flows either in vacuum or in some non-conducting medium. Fine. These two are the points of difference between conduction current and displacement current. There are two similarities also. Between conduction and displacement current. First point of similarity, they both have unit ampere. They both have same unit, that is ampere. And what is the second point of similarity? They both produce magnetic field. These are the 2 points of similarity. And now we go for very important article about Hertz experiment to generate electromagnetic waves. After prediction made by Maxwell about existence of electromagnetic waves, it was Mr. Hertz who had first of all proved the existence in laboratory, and that was done 32 years later after the prediction of Maxwell. What was the experimental setup in Hertz experiment? I am showing you. We have alternating voltage source which is first connected to one device which is called induction coil. Using induction coil, we can obtain very high alternating voltage changing with high frequency. That sort of device is known as induction coil. This is the circuit symbol for that. The output of induction coil is given to two linear rods, say M and N. Two linear conducting rods, they are M and N. And these rods are now attached with two big size conducting spheres. Fine. There is a very small gap between pointed ends of these two rods. Through this gap, spark is going to pass alternatively from upper end to the lower end and then from lower end to upper end. Because through this gap, there is a spark which is passing alternatively. We call that gap as spark gap. What is that spark? How it is produced? Not explained in the textbook. I will explain to you. Wait. This is all about experimental setup. Okay. Now just consider this direction. Correct? In the space, you just consider this direction. Let it be x-axis. Okay. Let this spark gap be at the origin and let this be positive x-axis. Fine. Now, the amount of electric charge on both the spheres go on changing periodically with time. How are those changes? I have shown nicely here using this graph. Tell me, what does this graph indicate? Upper part of the graph shows positive value of the charge on the second sphere and it is from 0 to t by 2. From 0 to t by 2, the potential on this sphere is positive with respect to this sphere, meaning thereby in this much time interval, charge on first sphere is negative, charge on second sphere is positive. I repeat, in this much time interval, charge on first sphere is negative, charge on second sphere is positive. But then, in the next half cycle, from t by 2 to t, it so happens that polarity is getting reversed. Now charge on this sphere would become positive and charge on this sphere would become negative. Fine. Now, as time passes on, what will happen in the spark gap? I am showing you. Tell me. First of all, from 0 to t by 4, the value of charge on both the spheres would increase. Here negative charge will increase, here positive charge will increase. Correct? Now, as this end becomes more and more positive with respect to this end, the potential difference between these two pointed ends go on increasing, which gives rise to some strong electric field. Fine. And when that intensity of electric field is very large, it so happens that some number of electrons are ejected out from this very end, because this end is high positive potential. Because bunch of electrons is ejected out, then after through this gap, this bunch of electrons are accelerated towards this end, which is positive. Correct? Fine. And because this voltage is changing with very high frequency, after very short time, again this end will become positive. So this bunch of electron would just move upwards. Again after very little time, this end will become positive, that bunch of electrons will move downwards. I mean to say, this bunch of electrons simply jumps up and down. It performs oscillatory motion in this spark gap. But why it is called spark gap? I am showing you. See, as this bunch of electrons is accelerated, say downward suppose, then they happen to collide with the atoms of air. And when they transfer their energy to the colliding atoms, you know what happens after that? In those atoms which receive energy, it so happens that electrons make transitions from lower energy state to higher energy state. But in higher energy state, they are not stable. So they would soon after that make transitions into lower energy states. And when any electron is making transition into lower energy state, you know energy will be emitted. So here energy is emitted in the form of visible light, which we can see. So there we get a flash of light. What do we get? A flash of light. That flash of light itself is known as spark. Correct? Each time whenever this bunch of electrons is either accelerated downwards or accelerated upwards, each time there is a spark produced in this gap. That's why we call this gap as spark gap. Fine. Now tell me, what will happen at these points on this direction? Correct? On this direction, at these points, what will happen? I am showing you. Just consider point A. Point A. At this very point, you just imagine unit positive charge. What you are supposed to consider? Unit positive. Just consider unit positive charge over here. Tell me, as time increases from 0 to t by 4, here negative charge will increase, here positive charge will increase. Fine. Charges on both the spheres go on increasing. This is negative charge sphere, and here you consider positive charge. So naturally there would be force of attraction. Negative charge sphere would attract this unit positive charge this way. So this is attractive force, correct? And here it is positive charge sphere, it would repel this unit positive charge this way, correct? And as these charges go on increasing, these forces would increase. Then what about their resultant force? Resultant force would be in this direction, that also would increase with time. Fine. But tell me, what is this resultant force? It is resultant Coulombian force, resultant electric force exerted on a unit positive charge. Because it is resultant electric force exerted on a unit positive charge, according to definition, we call it electric field vector E. Fine. So electric field in this direction goes on increasing from 0 to t by 4. But then after from t by 4 to t by 2, what will happen? Charges on both the spheres would decrease. So this resultant Coulombian force also would decrease, and then electric field goes on decreasing. Finally it will become 0 exactly at time t by 2. Fine. Later on what happens? In time t by 2 to 3t by 4, charges on the spheres have been reversed in polarity. This charge would become now positive, this charge would become now negative, and the amount of electric charge will go on increasing. Tell me, if this becomes positive, it would repel this positive charge this way, correct? If this becomes negative, it would attract this positive charge this way. So I mean to say, from t by 2 to 3t by 4, as the charges on the sphere go on increasing, this Coulombian forces will go on increasing. Resultant Coulombian force on unit positive charge in downward direction will go on increasing, correct? Which is nothing but electric field. So electric field increases in downward direction. Fine. Exactly at 3t by 4, electric field in downward direction would become maximum. But then after from 3t by 4 to t, it so happens that charges on both the spheres go on decreasing. So resultant electric field will also go on decreasing, correct? Fine. So I mean to say, at this very point, as this alternating voltage finishes one cycle, at this very point, this electric field first of all increases from 0 to maximum in one direction, becomes maximum, then after it decreases from maximum to 0. After reverting the direction, again it increases from 0 to maximum in opposite direction. and again it decreases from maximum to 0. Tell me what this electric field vector has done. It has finished one oscillation. It has finished one oscillation. Fine. Now tell me, at the same moment, at the same time, if you think of distant point which is further from point A is closer to this spark gap, we consider another point which is further than point A, let it be point B, then you know Coulombian force is inversely proportional to square of distance. As distance would increase, Coulombian forces would decrease. So when Coulombian forces here are of such magnitudes, here at the same moment of time, Coulombian forces will have less magnitudes, so electric field will be also less. But there also, electric field will oscillate periodically this way, 0 to maximum, maximum to 0, 0 to maximum, maximum to 0. But whatever is the amplitude of oscillation here, lesser than that will be amplitude here. As distance increases, amplitude of oscillation goes on decreasing. Now tell me, here is electric field which goes on changing periodically with time. Then don't you know, time varying electric field will induce magnetic field, and here magnetic field is produced because of time varying electric field. You know in which plane? In a plane exactly perpendicular to electric field. Electric field is at present produced in the vertical plane, which is oscillating. Electric field is oscillating, look, parallel to the length of these rods, okay, fine. And now magnetic field is produced in just mutually perpendicular plane. Perpendicular to vertical plane is horizontal plane. So magnetic field is produced in the horizontal plane. You know what happens in the horizontal plane at this point? As electric field is oscillating on upper side, at the time magnetic field is oscillating in a side towards you, towards the observer, say along positive z axis, means when electric field is oscillating on upper side, magnetic field remains perpendicularly outward from the plane of the figure, because we notice that direction of propagation of these waves is in the direction of vector E cross vector B, Right now this wave is going to propagate in this direction, away from the source, okay. Now this direction I have taken as x-axis. Now tell me, if electric field is this way, then magnetic field must be perpendicularly outward, then only vector E cross vector B, will be along positive x-axis. I am showing you how. Look, this pink colored arrow, it indicates electric field. This blue colored arrow, correct, this one, perpendicularly outward, that's why I am putting dot. In textbook they have shown wrongly, they have put here cross, it is very wrong, because if you take cross sign, means perpendicularly inside, then vector E cross vector B will be in this direction. No, it is wrong. Look, when vector E is oscillating on the upper side, vector B is oscillating in the outward side, correct? Perpendicularly outward from the plane of the figure. This is vector E, this is vector B. Now tell me, what is direction of vector E cross vector B? Direction of vector E cross vector B will be like this. Like this. Like this means what? Towards positive x-axis. That is why this wave will propagate along x-axis this way, away from this spark gap. Got it? Fine. Now what happens to the oscillation of magnetic field? As electric field continues its oscillation, it induces time varying magnetic field also. When electric field is oscillating this way, look, at that time magnetic field is oscillating this way, perpendicular outside and then coming this way, correct? And then after, when electric field is oscillating in the lower part, at that time magnetic field is perpendicularly inside. Again, look, magnetic field is inside and electric field is downward. This is vector E, this is vector B. Find out vector E cross vector B. Vector E cross vector B will be like this, right, this way. again the direction of propagation will remain same, correct? Fine. Now tell me, because here electric field and magnetic field are oscillating in mutually perpendicular planes, we call these waves as electromagnetic waves, because there are two fields, electric field and magnetic field, which are oscillating in mutually perpendicular planes. We call such waves as electromagnetic waves. Look at this diagram now. See, this is vector E, suppose. This is vector E, this is vector B, and this is the direction of propagation, correct? Any two of these three remain mutually perpendicular, and direction of vector E cross vector B at any point of time must be in the direction of propagation of electromagnetic wave. Okay, fine. Now tell me here, what this bunch of electron is doing here? It is oscillating up and down, and when it is oscillating up and down with very high frequency, it gives rise to some sort of disturbance which we call electromagnetic disturbance. And because the disturbance is produced here in the spark gap, it is likely to move away from it. And when this electromagnetic disturbance moves away from this gap, it gives rise to production of electric and magnetic fields in mutually perpendicular planes. And then after, we have given the name to such waves as electromagnetic waves. Okay? Tell me, in this experiment, which energy is transferred into which energy? This oscillating charge has kinetic energy, and ultimately that energy is emitted in the form of energy associated with electromagnetic waves, which we call radiant energy. So kinetic energy of oscillating charge in the spark gap has been ultimately converted into radiant energy. This is the principle of working of this device. Okay, fine. Now tell me, consider a point which is on this direction of propagation, and just consider one plane which is perpendicular to direction of propagation. Fine. That plane is this. Now in this plane, at this very point, you know what happens? E vector is oscillating this way, up and down, and B vector is oscillating this way, outside, inside, outside, inside. When E vector is oscillating on upper side, B vector is oscillating on the outer side. When E vector is oscillating downward side, then B vector is oscillating inside, correct? Vector E and vector B remain perpendicular during their oscillations. Fine. As long as electromagnetic waves continue to pass through a given point, it so happens that electric and magnetic field oscillate in mutually perpendicular planes, that too periodically. Okay? And with direction of vector E cross vector B remaining in the direction of propagation of wave. Got it? Fine. Now, these rods are compared to inductors, and this pair of spheres is compared to capacitor, and then this whole arrangement is taken as equivalent LC circuit. Equivalent LC circuit. Why it is called equivalent LC circuit? Because from LC circuit also, you know, in LC circuit charge continues its oscillations, and an oscillating charge performs an accelerated motion, and it was Mr. Maxwell who had proved whenever any charge performs accelerated motion, it simply emits energy out of it in the form of radiation, in the form of electromagnetic waves. So in LC circuit also you have generation of electromagnetic waves, and here also you have generation of electromagnetic waves. That's why this whole experimental setup, pair of inductors and pair of this capacitor, it is taken as LC circuit. Actually it is not LC circuit, but it is taken as if it is equivalent LC circuit, because from here also and from LC circuit also we get emission of electromagnetic waves. Got it? Electric field is oscillating in vertical plane. That's what I have shown here with the help of pink arrows, and magnetic field is oscillating in horizontal plane, that I have shown here with the blue arrows. But this is the situation at different points along x-axis at a given point of time. At some other instant of time, the magnitudes of these vectors would be different. This diagram is for a particular moment of time. Got it? Fine. Even after having production of these electromagnetic waves, Mr. Hertz was not quite sure regarding production of these waves, because these waves are invisible. They do not contain any materialistic particles. They do not contain any charge in it. So these waves, which are invisible, how to prove their existence, how to give evidence for their existence? Mr. Hertz had applied one very good idea. He wanted to verify. You know what we had done? This point is not there in the textbook, just look here. He had placed one metallic ring, correct, having these two pointed ends very close to each other, and between these two ends there is a very little gap. Now just imagine that in this experiment really electromagnetic waves are produced. Just consider, when electromagnetic waves are passing through these points, you know what happens? Magnetic field is oscillating inside and outside this way. When magnetic field is oscillating inside and outside this way, you can say magnetic flux linked with this ring would change periodically. And if magnetic flux linked with any ring changes with time, you know what will happen? You will get induced EMF. Between these two pointed ends, you will get some induced EMF. And suppose this end becomes positive, this end becomes negative, then spark should pass upward. If this end is becoming positive, this end is negative, then spark should pass downward. I mean to say, you should get production of sparks in this very little gap. Mr. Hertz had kept this ring, and really he had noticed that sparks are produced in this gap also alternatively. Then he had to believe that here there must be induced EMF. It is because of time varying magnetic field, and time varying magnetic field is due to time varying electric field. So here both the fields are present, electric field as well as magnetic field. That's why he got the existence, he had proved the existence of electromagnetic waves indirectly using this ring. Got it? Fine. So my dears, this is all about the experiment performed by Mr. Hertz, and he had verified all the three predictions of Maxwell. Just recall those predictions, that there must be existence of electromagnetic waves in our day-to-day life. Then second prediction was the velocity of electromagnetic waves in vacuum must be 3 into 10 raised to 8 meter per second. And third, light waves also must be electromagnetic waves. All the three predictions he had proved correct. Correct? One more thing. Tell me, how are the oscillations here? Electric field and magnetic field oscillate in a direction perpendicular to direction of propagation of wave. Because oscillations are perpendicular to the direction of propagation of wave, such waves are called transverse waves. Such waves are called transverse waves. And because these waves can pass, can propagate even in vacuum without the presence of any materialistic medium, such waves are called non-mechanical waves. You have studied in second semester, for any wave, for propagation of any wave, if medium is not required, such wave is called non-mechanical wave. For the propagation of such waves, we do not require any medium. That's why these waves are non-mechanical waves. So electromagnetic waves, remember, they are transverse waves also, and they are non-mechanical waves. And one thing more, with whatever frequency this charge is oscillating here, with the same frequency we are going to have emission of electromagnetic waves from this spark gap. Okay, fine. Come on, my dears. Just now we have understood the generation of electromagnetic waves from spark gap in Hertz experiment. Now, in those generated electromagnetic waves, we find two types of electromagnetic components. Which two types? Let us see them in detail now. One type is called inductive components. Another type is called emitted or radiated components. What are the points of difference between them? I am showing you. In both, no doubt, electric field and magnetic field oscillate periodically in mutually perpendicular planes. That is true. But then there are some points of difference which you must remember. Look, here these inductive components are those components which remain attached with this spark gap. When they remain attached, they are not separated from the spark gap. Okay? And these are those components which have been already separated from the spark gap, or they have been detached from the spark gap. Okay? These components remain attached, these components get detached from the spark gap. Okay? Second point of difference is that because these components are attached to the spark gap, they have not yet come in motion. They do not move. Okay? And here these are the components which have been emitted, which have been thrown out, which have been radiated. That's why they will start moving. They will start propagating in the vacuum with a speed, practically we find 3 into 10 raised to 8 meter per second. Okay? Now look in the figure carefully. When value of vector E becomes maximum at the same point at the same time, value of vector B is 0. And then when value of E becomes 0, value of B becomes maximum. Tell me, both of them are performing oscillations. When electric field is maximum, magnetic field is 0. When electric field will become 0, magnetic field will become maximum. When this will become maximum, this will become 0. When this will become 0, this will become maximum, like that. So they are performing oscillations with a phase difference between them equal to pi by 2 radian, equal to pi by 2 radian. That's what I have noted here. Phase difference is come on pi by 2 radian. Got it? And here look in this figure carefully. When vector E is 0, vector B is also 0. When vector E becomes maximum, vector B also becomes maximum. Meaning thereby, both of them perform oscillations with the same phase, because when vector E is 0, vector B is also 0. When they become maximum at a time. Both of them become 0 at a time, becoming maximum at a time, becoming 0 at a time. I mean to say they perform oscillations in phase. In phase means having node phase difference, that is mathematically phase difference is 0. Phase difference is 0. Here phase difference is pi by 2 radian, here phase difference is 0. Here look in the figure, vector E and vector B values, they decrease very rapidly, quickly with the distance. According to this relationship, values of E and B decrease with the distance according to this relation. Come on, E varies as 1 upon r cube, B also varies as 1 upon r cube. So they both are inversely proportional to cube of distance, inversely proportional to 3 power of distance. Okay? Here also vector E and vector B, they decrease with distance, but slowly according to this relationship. E varies as 1 upon r, B varies as 1 upon r. Values of E and B are inversely proportional to distance. Fine. Now let us talk about Hertzian dipole. In textbook, Hertzian dipole, they have described in a wrong way. The experimental setup of Hertz experiment, they have compared with LC oscillator circuit. That is true. But same thing they have said as Hertzian dipole, it is very wrong. Hertzian dipole is not that. See, in Hertz experiment, the amount of electric charge and polarity of electric charge on the two spheres were changing periodically with time. Here in Hertzian dipole, charge and polarity are not changing. See, we take a pair of spheres, we just attribute fixed amount of equal and opposite charge on both the spheres. They do not change with time, neither polarity nor magnitude. And then after what we do, we just give them oscillations. And we give them oscillations this way, such that the distance between them changes periodically. And then this is a construction which is called Hertzian dipole. Hertzian dipole. Now in this Hertzian dipole also, you must have noticed that these two charges are performing oscillatory motion. And whenever any charge is performing oscillations, meaning thereby it performs an accelerated motion. And don't you know, Mr. Maxwell had proved whenever any charge performs an accelerated motion, it radiates energy out of it in the form of electromagnetic waves. That is how we have generation of electromagnetic waves from this Hertzian dipole. Okay. Remember this very short formula which is applicable to all the waves. C equals to F lambda. Normally we write here V equals to F lambda. That is the formula you studied in second semester. V or C means velocity of wave. Here F means frequency, lambda means wavelength. But because electromagnetic waves in vacuum, they have velocity equal to 3 into 10 raised to 8 meter per second, which is normally shown by symbol small c, correct? C is velocity of electromagnetic waves in vacuum, F is frequency, lambda is wavelength. Then remember, it was Mr. Jagdish Chandra Bose, Indian scientist, who had generated electromagnetic waves in laboratory having wavelength ranging from 5 millimeter to 25 millimeter. So this is the range of wavelength. The corresponding range of frequency may be getting asked in the examination. What you should do? Look, C value, it is 3 into 10 raised to 8 meter per second. Then frequency you require. First of all, put maximum value of lambda, that is 25 millimeter. Put it here, 25 into 10 raised to minus 3, because millimeter you must convert into meter. And then you will get minimum value of frequency because you are putting maximum value of lambda from these two values, correct? And later on, you may put this minimum value of lambda here, convert it into meter, and then find out frequency. At that time, frequency would be maximum. Then you are getting two values of frequency. One is minimum, one is maximum. So you can mention the range of frequency from minimum to maximum. Got it?